All right, guys, we're jumping to free fall. Free fall. What's one thing nice about physics is it's just a continuation of what we talked about already with acceleration. The chapters really build on each other. So those equations should look familiar to you. They're written a little differently, but it's the same. That's d equals vit plus 1 half gt squared. We put a little subscript y with the d to represent vertical motion. So free fall is taking place vertically. And free fall itself just means free, it's fall, sorry. Free fall is falling under the influence of gravity only. So you can think of it as free of air resistance. And so these equations are assuming that you're in a vacuum, that there's no air resistance. They do work on Earth, but they would be approximations. Now, if you're doing a book versus a piece of paper, the it's going to work for the book. It's not going to work for the piece of paper. But obviously, air resistance would affect this piece of paper more than the book. So there are limitations to it. But out in space, on the moon, perfect. Like they are perfect. So it is air resistance does cause some problems, but short distances with normal objects, these are good to go. So again, we're subscripting everything, not everything, but some of the variables are subscripted with a y to specify that it's up and down. Now t is time; it doesn't have a direction associated with it. The acceleration was changed to the acceleration due to gravity, which is little g. I'll talk about that variable in a little bit here. The only other notation that's weird, you notice it's missing VF and VI. So instead of saying final and initial VI and VF, which are relatively vague, right? We don't know, is it left and right? Is it up and down? Is it at the beginning? Or we do notice the beginning or end, but what time is it actually happening at? So VY naught is weird to say, but it's V is how fast, Y is vertically. So how fast vertically, and that zero means at time zero. So that's very specific. How fast? Vertically at time zero. You can see why that's initial. Now the Vy without the zero is our good old VF. Um, so on that note, you can at this point in time use the subscripts you like, but it should be similar to what I've presented. Like the dy, either you're using d or d sub y. When we get to projectiles, though, you're gonna have to specify is it dy or dx. So I would habit wise, I would start doing it now, but I won't push it till the next unit. In the v equals d over t, could we use a constant motion equation with free fall? Well, free fall is defined as falling free of air resistance, so it's constant acceleration. Constant motion has no acceleration, so in that aspect, no. If there was some air resistance, like this piece of paper does hit its max speed, right? Its top speed, and we'll talk about that in this unit too. In that case, you would use v equals d over t, or you could use v equals d over t. All right, Galileo, father of physics. There's going to be handful of videos on this that I can't show you because they'll flag me for it. Uh, but email me if you want the links. I'll send it to you. So the video, I'm gonna run down with. Sorry, guys. What the videos show, basically. I'm gonna at least describe it to you. So Aristotle, we're talking 300 BC, over 2,000 years ago, said heavier objects fall faster, which is right, true, right? If I drop this piece of paper, the book wins every time. Like there's no weird situation where the book doesn't win. So that made sense. Motion needs constant force, like your car. To keep your car going, the wheels got to keep pushing on the road. Like that made sense. His method was just observation, reasoning, logic. Like just I see it, that makes sense, and that's it. And then that dominated for 2,000 years because no one really questioned it, and it's what we saw. Sorry, it's what we saw. So Galileo comes around in the 1500s. So again, right, thousands of years later, Galileo comes along and he says all objects fall equally when there's no air. We'll talk about that. Inertia keeps objects moving. We'll talk about that. He's saying you don't have to keep something push. You don't have to keep pushing something. If you push it, it will just keep going. But then there might be something else that slows it down. We'll talk about that when we get into forces. He uses experiment and math, right? Which involves observation and reasoning. But he actually took notes, like kept track of experiments, like verified it with some math. He is the start of what we're studying, and then that's modern science. So we are uh, really starting with Galileo. And then just a quick quick, why did it take science and math a hard time to overthrow Aristotle? Well, just for 2000 years we've been told this is what has happened. This is science, right? For 2000 years we had this science book that like explained everything to everybody. That's hard to get rid of, especially when it's grained politically, religiously, even among the people. Like it was ingrained with everybody. So Galileo had to be careful how he couldn't just come out and say like Aristotle was wrong. So he kind of chipped away. He published some books. He started showing people like, hey, if you take your telescope and point it up, the moon is not a perfect sphere. They thought the planets were like perfect, like celestial, like heavenly spheres, like that space was somehow different than Earth. And he started looking and he's like, it's just doing the same thing. It's following the same rules. The other thing is a lot of, at least in Europe, a lot of the if you were educated, you were learning or went to school, you were learning in Latin. um, and then the common people were well, if you were in Italy, where Galileo was, it was Italian. He wrote a lot of his stuff in Italian so that everybody could read it. He didn't have to be upper class. Everybody could read it. And then one of his books, he had a handful, but dialogue concerning two chief world systems. He instead of just coming out and saying this is what I think, and like throwing it in people's faces, he had three characters. Salviati was represented kind of his viewpoints. Well, the big one, the heliocentric. We weren't the center. That space wasn't some special place that we couldn't understand, or that the laws of physics, like on Earth. So that was Salviati. Simplicio, which I enjoy the name, right, was your simple-minded person that was not willing to change their viewpoint. Like was like, this is what I've been told. This is what I'm going with. I don't care for what you're showing me. Like that was one person. And then Segredo, I don't know if I'm saying this right, sorry, Italian people, um or at least Italian people who can speak Italian. The My pronunciation is probably awful. An open-minded layman. So your run-of-the-mill person who's intelligent, and does question things, so is interested. And then that conversation bounced around those people, and he was able to give his viewpoint. Now the church, being the church, was on to him, and they were like, "Hey, we told you not to, we told you not to do this." So he didn't. He was not. He was so this is the Catholic Church. He was friend with the popes. He did not want to be excommunicated. He did not want to have a fight with the church. That was not his intent. So some of the stories about him fighting with the church, not so much. From my understanding, he was trying to publish his stuff without angering them. So sometimes he did bend their rules a little bit, but uh, he was eventually able to change their minds, but it took like 200 years. Uh, so so he was gone, but he did eventually change their mind. Some of what we know about Galileo, this is interesting, is through letters with his daughters. That we still have letters from 500 years ago is crazy to me. But she ended up becoming a nun and took the name Maria Celeste. And I just thought it was interesting with the name Celeste that it has that it's heavenly, right? It's I don't know if it's Latin. I think it's Latin for heaven. Well, it's definitely something with heavenly, but it's either Latin or Italian. Uh, that So it took into her religious views, but also her father's views about the heavens and space. So it was interesting. So Galileo and gravity. Sorry, my little tangent on Galileo. So until Galileo, heavy objects landing first was our understanding of gravity, which again, it makes sense. I drop a book and it lands first before that piece of paper. So what Galileo does is he actually starts, because you can drop stuff, but it happens so fast you can't really tell. He didn't have slow motion cameras, right? There was no way to slow it down until he realized he could roll things down hills, and then that would still be gravity accelerating it. He could just slow their effects. So he rolled different sized spheres down hills, sorry, and started to notice that they all accelerated at the same rate. Didn't matter if it was small, little. Uh, he realized air resistance was causing them to fall differently. So if I take the book and put the piece of paper on top of the book, then I can block the air from the piece of paper, And if Aristotle's right, the book falls faster and the paper falls less fast and they separate. If Galileo's right, that piece of paper stays right on top of the book the whole time it falls. And that is exactly what you see. I would try it if you don't believe me. But also, so just to put another knock against that, we have to separate air resistance and gravity. So if you ball up that piece of paper from short distances, this won't work from far, but from short distances, they fall together. So just another, he's the first one to realize that. Now, when air resistance does affect things, we get this thing called terminal velocity. Another video I can't show you, but again, email, message me if you want the links. The and you can probably find this. They back in the 2000s, multiple people have done this. This is the one with the best footage, like the high def footage. They did it in the 60s, and it was like old grainy film. This was recorded in high def. He went up in a hot air balloon above our atmosphere, way above our atmosphere, and then just jumped out. And so for minutes, right, very little atmosphere, he's just going faster, 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 faster. It breaks the sound barrier. Like goes, I think he maxes out at like 800 miles an hour. And then he starts to hit our atmosphere, and he starts to slow down. They have all these gauges on him, like that are measuring stuff about him, like his speed, his acceleration, all that stuff. But you see his speed start to go down, 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 down. That's him hitting our atmosphere. And as he slows down, he eventually reaches terminal velocity, which for us is around 100 to 200 miles an hour. Now he's falling at a constant speed, and then he just keeps falling, falling. Eventually, he gets close to the surface of the Earth. He throws his chute. Again, air pushes up on that chute. He accelerates to a constant velocity, reaches terminal velocity again, and then with the chute open, it's like 10 miles an hour is our terminal. Well, it's the chute's terminal velocity, and then you land just on the ground. You're good to go. Walk away. But that's so terminal velocity is an issue with air resistance. Get rid of air resistance. Now we're talking vacuum, and we don't have this problem anymore. So which object lands first when the effects of air resistance are not a factor? All objects land at the same time. So they did this experiment. We can do it on Earth with vacuum tubes. Sorry, I don't have video of this. I will. I'll have to see if I can start recording demos for you. But there are plenty of videos of it. But the so on Earth you can do it. You can create a vacuum tube. We can take a whole room and pull out the air, like that kind of stuff. So when they were doing moon landings, the astronauts actually brought out a hammer and a feather and they dropped it, and they fall perfectly together. Like it's just you just don't expect it. I mean, we knew it was going to happen. You still don't expect it. And then this is a side question: can you float off the moon? No. Gravity is lower on the moon, but is not non-existent. You can't just jump off the moon. This picture over here with the gravity boots came out of one of my kids' books. Gravity keeps us on the ground. That is true, but there's not a lot of gravity on the moon. Also true. Still has gravity, just right, not as much as we do. So astronauts wear these boots to stop them from floating away. No, you know the boots are just part of the spacesuit to keep you pressurized, to keep you safe, right? To keep the air inside your suit. They are not to keep them from floating away. They are not special like heavy boots that keep you from floating away. Like that, I don't even know why someone thought that. There's another video. The how we tested our shuttles and still test some of the stuff we're sending out into space to make sure that it can withstand that the vacuum. It's a giant vacuum chamber. Sorry guys, I did not mute my phone. Acceleration due to gravity lab. It's an extension of the acceleration lab. So you're going to do what we did in the acceleration lab, but specifically to figure out gravity, the acceleration due to gravity. So that's coming. Acceleration due to gravity. It's the lower, so the variable for the acceleration due to gravity is a lowercase g. We are going to specifically use 9.8 meters per second squared, nothing else. If you're looking stuff up in other books, you're watching other videos, like they might use other AI for this instance. We are using 9.8. So if you use anything else, I'm kicking the problem back to you because you got to use what we're doing. We won't use our units in feet. It's 32 feet per second squared. Both of these are hard to visualize. Like 9.8 meters per second squared means every second your speed's increasing by 10. So 10, 20, 30, 40, your speed keeps increasing. 20 miles per hour, though, I think most of us can picture. not too fast in a car, pretty fast for running, but so if it's 20 miles per hour every second is what gravity is for us. So every second of fall, you're going 20 miles an hour, 40 miles an hour, 60 miles an hour. Your speed's increasing by 20. And again, how can all objects fall at the same rate regardless of weight? Well, you get rid of air resistance, then all that's affecting them is gravity. Gravity pulls on an object's mass. So the more mass you have, the more weight you have. And what happens is as the mass goes up, the weight goes up. Mass goes up, weight goes up. Like um they go up together. And when you take you take the ratio of weight over mass or weight divided by mass, you on Earth at least, you get 9.8. This is satellite images or a satellite image of the variations in our gravity, and you can see where it's redder, it's higher concentrations of gravity, and this is the Andes, right? Mountain range, stone, heavy, just rock, right? It's going to be higher, it's going to be heavier. There's more land mass there to get a higher gravitational field. It also varies by elevation. So it's not the same everywhere. New York at sea level is 9.803. San Francisco at sea level, 9.800. Denver a mile up, it gets less, 9.796. Pikes Peak, go even higher, 9.789. Still not much difference between 9.8. You can actually follow this little chart here, this graph, but go up hundreds of miles an hour. Here's 150 miles up where the space shuttle orbits, still around 9, right? It's 9 something, 9, 200 miles up, still 9 something. It drops, but not crazy fast. Now you go thousands of miles up, then it starts to plummet. So at like 5,000 miles, we're around 2 meters per second squared. 10,000 gets lower, it gets lower. Gravity will never actually be zero though. It approaches zero. It gets really close to zero, but never. It's the limit. It just approaches zero. It never actually hits it. Concepts. So amplify free fall symmetry practice. This is a quick little activity that kind of, I don't want to say it, quick little activity to just get you used to free fall. It kind of walks you through everything. Obviously, ask questions if you get stuck on it. The factor of change, free fall factor of change. You watched the factor of change method. I'm not going to force you into it, but you watch that video. It's just a way to answer these questions. They're going to start showing up more in chapters. Email me if you're not sure, if you want more practice with it, but we're going to do one now here. But if the time of fall is doubled, by how much does the displacement of the falling object change from rest? Like that's hard to visualize what's going on. So that whole little ed puzzle I gave you on factor of change is just a quick way to do it. So I got time, displacement, from rest, that's a VI. Uh, and then it never mentions anything about VF, never mentions anything about the final velocity. So you can narrow down the equations. Well, it can't have final velocity in it because I have no idea. There's no mention of final velocity. So you're not actually doing like relative math, like not actually putting in real numbers, but like factors of numbers. That's why it's called the factor of change method. So dy is what we're looking for. Vy naught, what did it start at? It started at rest. So this whole part is 0. 1/2 never changes. It's a constant. So that becomes a 1. If you want more details on why this works, we're doing math. We're kind of shortcutting the math is what's happening. But 1/2 becomes a 1. Anything that doesn't change becomes a 1. So 1/2 becomes a 1, g becomes a 1, and you're left with t squared. Well, time doubled, so 2 squared is 4. So your displacement actually increases by 4. That is not something you should have in your head. So the method is just a way to answer these typical physics questions with a little bit of using like a shortcut math instead of trying to process what's going on. Practice free fall, reaction time, infinite acceleration. All right. Some of this stuff we're not going to do. Maintaining orbit. I'm going to talk about it real quick. So what happens when an object is thrown fast enough tangent to the Earth? You can go. So the question I kind of glossed over in a couple slides there. Is infinite acceleration possible? Like, can you just accelerate forever? If you were falling straight down to the Earth, right, you're going to hit the surface eventually. But what if you went sideways to the Earth? And if you were going fast enough sideways, as you fell, the Earth wouldn't be below you anymore, and you could circle the Earth. And then that's an orbit. And so what we do is we get the space shuttles, or the satellites up to like 18,000 miles per hour, and we launch them not straight up, but sideways, like this picture is showing. Once it hits 18,000 miles per hour, it's going fast enough sideways to the Earth. We can shut that off, and gravity just pulls it down into an orbit. Just gravity keeps just pulling it down, pulling it down. But it's so far away from the Earth, it doesn't actually fall back down to the Earth. Um, and then Galileo, I want to say it was Galileo. It could be Newton. We're talking 15, 16, 1700, somewhere around there. I can't remember exactly who drew this picture. But um, kind of rationalize, like, if you threw something, it falls. Throw it faster, falls. Throw it faster, falls. Throw it fast enough, it's going to fall, but it's going to fall around the Earth. So we've known its potential for a while, but we're not able to do it until, I don't know, the 50s and 60s, like that kind of time frame. This is a space shuttle launch. It'll flag me if I show you any of these videos. This is a video of the space station orbiting. It's pretty cool. The space station is pretty big, like the size of a football field. But I mean, it's not all living space. It's just these living quarters. But with the solar panels and all that, it's huge. It's big. Floating in space. So we call it zero G. But is it really zero gravity? Earlier on, I said there is no such thing as zero gravity, right? It approaches zero. So what happens is you get what appears to be no gravity. But what's really happening? So are the astronauts really floating in space? Is gravity really zero? Gravity's not zero. It can't be zero. Are they lighter? Does air change because they're out in space? No. How do you float? You're less dense than the medium you're in. Well, we don't become less dense just because we go up into space. So how do we have this thing called weightlessness and zero gravity if gravity can't go away? So the question I'll pose at you is, can you weigh yourself while falling? And you can't, right? You can't. To weigh yourself, you got to step on a scale. Well, the scale pushes down on the ground pushes back up on you, and the scale gives a reading. If you're falling with the scale, you can't push on the scale, and then that's what's really happening. You are in a constant state of free fall, and you can't push back on any of your surroundings. So it appears as though gravity shut off. I'm going to try to, hopefully I don't ruin this. I'm going to come back. Let's save it to the end just in case I ruin it. But so we can simulate free fall. We don't have to go up into space. They can take airplanes, and then this plane goes up and then follows these arrows. So as everything's going up, everything in the plane wants to go up. And then all of a sudden it levels out, but everything inside keeps going up. And then, right, everything's in the plane's going up. All of a sudden the plane levels out. Well, everything inside's still going up. Not long, for like 30, 40 seconds. And then you start to fall and the plane catches you on the other side. And so we can simulate free fall in space with an airplane. Oh, this is the last slide. All right, let's see if I can play this video. So this is one I made, so it's hopefully not going to flag me. It would help if I knew what I called it. Slow motion weightlessness. Here we go. Hopefully this records okay. We'll at least be able to see it, and I'll talk.
All right, right now, what you're looking at is a scale, and I know it's a little...
Here, I'll mute myself. Right, the scale. So it's at 5 pounds. And all I'm going to do is pick it up and drop it. And I'm being weird. Hopefully this is recording okay. You saw it go to 0. It happens real quick. Here, we'll watch it for another second here. The video feed is slow and weird right now. But you'll see it drop to 0 every time I drop it. Sorry, it's real quick. I think the last drop I do in, I don't know if it's going to show it to you, in slow motion. This must be it, hopefully. Maybe. Oh, all right. Sorry, guys. It seems to be freezing out. I'm going to stop it. See how this goes.